Hello everyone and welcome back. I'll be covering a new topic called as deadbeat response. Uh, Deadbeat response is specifically used to reduce your oscillations. Like let us say there is a plane and there are some poles and zeros that I've plotted over here. Okay, these poles and zeros will oscillate before they reach a certain point and become constant. There will be a peak, overshoot and everything, and other different poles and zeros will oscillate and reach a constant value after certain time period. Each pole and zero will have their own time period or number of samples before which they become constant. Deadbeat response makes sure that all these poles and zeros become a constant value after finite samples. Let us say there is a sample t, 2t, let us say there is at 2t. All of these will oscillate, and after 2t they will become constant. Every one will oscillate and after 2t they will become constant. Deadbeat makes sure that everybody becomes constant after a sort of finite samples. So let us dive into deadbeat. Okay, we have a generalized block diagram for the deadbeat response. We have R of Z, E of Z, DC of Z, GD of Z, C of Z, and a unity feedback, which is negative feedback. Okay, now there are two methods by which we can find the deadbeat controller, that is a digital controller. All the controllers and all the responses in a deadbeat response are all in digital format. We need to find what will be the deadbeat controller. It will be the transfer function of deadbeat controller for a certain given input and a plant. Okay, there are two methods. First method, that the transfer function given GP, the transfer function given in GP, it will have some poles and zeros. Those poles and zeros will all the poles and zeros will lie inside the circle, or some will lie on the circle, outside the circle, or both. Okay, so there are two methods, both are different. The method of solving for finding DC of Z is also different. First we'll look at when all the poles and zeros lies inside the circle. Okay, we have three formulas for it, out of which we'll be using only two, and both these formulas will be used in both the methods, but only the values to find out the values, the method will be different. Okay, first formula is M of Z is equal to Cz upon Rz. That means our transfer function output upon input will also be called as M of Z, and it will also equal to DC of Z GP of Z upon 1 plus DC to Z GP Z, because you have a unity feedback. It is also called as GZ upon 1 plus GZ H of Z. Okay, this will be the transfer function for this, but we know that what is G of Z. G of Z is nothing but DCZ into GPZ. H of Z is 1, and replacing those values you get this transfer function. Okay, so Cz upon Rz is equal to M of Z, and it is also equal to DCZ GPZ upon 1 plus DCZ GPZ. Now what is DCZ? We'll use this equation and we'll equate it to M of Z, and we'll find what is DC of Z. So we get DC of Z is equal to 1 upon GP of Z into M of Z upon 1 minus M of Z. Okay, error function is nothing but R of Z minus C of Z. We know what is C of Z from this equation, so we can substitute that and we get E of Z is equal to R of Z upon 1 plus DCZ GPZ. Okay, now as I said, the condition that we are looking at is when all the poles and zeros lie inside the circle and none of them lie outside the circle. Then we have a fixed value for M of Z. There are two types of inputs for which the entire sum will be solved. First will be the step input and the other will be the ramp input. For step input, we know that R of Z is nothing but Z upon Z minus 1, because it's a step input, so input will be Z upon Z minus 1. For that, M of Z will be equal to 1 upon Z raised to N. Now what is this N? I will discuss it later. Okay, just remember that for step input, the value for M of Z is 1 upon Z raised to N. It's a fixed value. Okay, and for a ramp input, R of Z will be equal to Tz upon Z minus 1 the whole square, we know that. And for that, M of Z will be equal to N plus 1 Z minus N upon Z raised to N plus 1. Now what is this N? N is nothing but total number of poles minus total number of zeros in the plant transfer function. What is N? N is number of poles minus number of zeros in the plant transfer function. From there we get the value of n. We'll substitute the value of n for the particular input, whether it is a step input or a ramp input. Depending on that, we'll substitute the values. Let's take up an example. We have been given GP of z is nothing but z plus 0.6 upon 3z square minus z minus 1. So we know that there we have a 1 0 and we have 2 poles, because this is a quadratic equation, so of course it will give you 2 poles, and this will give you 1 0 at minus 0.6. Okay, so for step input we know r of z is nothing but z upon z minus 1, and m of z will be equal to 2 minus 1, that is 1. So 1 upon z, that is equal to 1 upon z. Okay, so we know what is m of z, we know r of z. Let us find out dc of z. So for formula for dc of z is directly given 1 upon gp of z into m of z upon 1 minus m of z. So we'll write that. We know what is m of z, we know what is gp of z. We'll substitute those values, we will solve it, and we get dc of z, that is the deadbeat controller's transfer function, is equal to 3z square minus z minus 1 upon z plus 0.6 into z minus 1. Okay, this is your dc of z. Now what is your c of z? What will be your output? We need to find what is the output also, the output train of samples. So we know that c of z is upon r of z equals to m of z. Now you have two ways of finding c of z. First you can equate this equation and this equation and find c of z, or you can equate this equation and this equation and find c of z. In both the cases you will get the same c of z. I would prefer to use this because this is much more simpler to solve rather than this, because in this you need to multiply dc of z into gp of z again and do the entire calculations and then multiply it with r of z. That is too tedious. Instead of that, you can just multiply these two and do it. This is much simpler. So I have taken c of z upon r of z is equal to m of z. I know what is m of z, I know what is r of z, so I substitute those and I have found c of z. Now c of z is equal to 1 upon z minus 1, which can also be written as z inverse into 1 minus z inverse the whole raised to minus 1. Okay, I can write this. Now as I said, I need to find a train of samples. Okay, so I know the Taylor expansion. Okay, we need to remember the Taylor expansion of 1 minus z inverse the whole raised to minus 1, which is nothing but 1 plus z inverse plus z raised to minus 2 plus z raised to minus 3 and so on. Then we multiply it with z inverse and we get this. So this is your output c of z. So you see that after one sample your entire thing will become constant. Your oscillation will curve and it will become constant. So if we have this, so this is 0, this is t, this is 2t and so on. So at t you will get the constant values. That means all the samples will have constant values. From 0 to t they will have variable values. From 0 to t they will have variable values, but after t everybody will have constant values. As you can see, everybody has their coefficients as 1, so everybody will have a constant value. Okay, from this equation we come to this conclusion. Okay, well, now the next thing is I have solved the same thing using a ramp input, and I am seeing that what will be the situation for this in the ramp input. What will be the output? What will be the train of samples in the output if I have a ramp input? For ramp input I know that r of z is nothing but tz upon z minus 1 the whole square. Okay, m of z is nothing but n plus 1 z minus n upon z raised to n plus 1. Now I know that n is equal to 1 from here. Okay, I'll substitute that value. So I get m of z is 2z minus 1 upon z square. Same formula, dc of z 1 upon gp of z into m of z upon 1 minus m of z. Substitute those values and get the transfer function of dc of z, which will be coming around 3z square minus z minus 1 into 2z minus 1 divided by z plus 0.6 into z square minus 2z minus 1. So that is my deadbeat controller's transfer function. Now I'll find the train of samples for the output. So for the output I'll use cz upon r of z is equal to m of z. I know what is m of z, I know r of z, so I'll find c of z. Now what is c of z? C of z will be this. Okay, c of z is given as t into 2z minus 1 upon z into bracket z minus 1 the whole square. Okay, t into 2z minus 1 upon z into bracket z minus 1 the whole square. Now I need to find the train of samples. So I've done all of this just to get to this. Okay, now how do I get this? Partial fraction, find ABC. I've taken t common because that's a constant value, it's not required over here. Find the partial fraction, get ABC. I got a as -1, c as 1 and b as 1. So I found out the transfer function as -1 upon z plus 1 upon z minus 1 plus 1 upon z minus 1 the whole square. Now I know what is the Taylor series for this. For this, that is 1 upon z minus 1 the whole square. Whenever you try to find the Taylor or Lorentz series, you always write it in the terms of z inverse. Only in terms of z inverse is the formula defined. Okay, I know what is the Taylor series for this. For this it is 1 plus 2z inverse plus 3z inverse plus 4z raised to minus 3 and so on. Okay, for 1 minus z inverse it is 1 plus z inverse plus z raised to minus 2 and so on. Okay, I'll multiply z inverse and 1 by and z raised to minus 2 in their particular brackets, and I get this. I already have a minus 1 upon z, that is minus z inverse, so I'll cancel that out and I get this series. Now z raised to minus 2 and z raised to minus 2 are added up to form 2z raised to minus 2. Z raised to minus 3, 2z raised to minus 3 becomes 3z raised to minus 3, 4z raised to minus 4 and so on, and it will be multiplied by a t outside. So as you can see over here, it's a ramp. Okay, so it will be forming something like this. Here is 0, here is t, here is 2t, 3t, 4t and so on. Okay, 2t, 3t, 4, 3, amplitude 2, amplitude 3, amplitude 4. Okay, coefficients, accordingly their amplitude. Okay, now 0 and t both will converge. It means that from 0 to 2t you will have all the oscillations. After 2t they will become constants in the form of a ramp. Okay, so that was the C of z. I've given a question over here. You can solve this and get the dc of z and c of z. This is the answer. You can try to solve it. It's the same method, nothing different in this. Okay, this was the method in which you had all your poles and zeros lie in the same plane. Same plane in the sense that means inside the circle. Sorry, the poles and zeros both lie inside the circle. Now what if your pole or a zero or both of them lie on the circle or outside the circle or both? Okay, in that case your formula for m of z and 1 minus m of z changes. The formulas remain the same. dc of z is nothing but 1 upon gp of z, m of z upon 1 minus m of z. This thing remains the same. Even c of z upon r of z is equal to m of z. This also remains the same, but the changes where occur is that m of z and 1 minus m of z both will have their individual values. Earlier we had defined m of z and we had substituted that value in this also. But now we have to find the value of m of z and we need to find the value of 1 minus m of z and then substitute those values and then find dc of z. That is the only extra work that we have to do in this, but that extra work is also very lengthy. Okay, first what we are going to do in this, that we need to cancel out those poles and zeros which lie on or outside the circle. Okay, so m of z should contain the zeros, because gp of z, when you write 1 upon gp of z, the zeros in the gp of z will be in the denominator and the poles of the gp of z will be in the numerator, right? So if your m of z should have the zeros which lie on or outside the circle so that they can cancel out with the gp of z's zeros, and 1 minus m of z should contain the poles which cancel out the poles of gp of z which are in the numerator when which lie on or outside the circle. So m of z must contain the factors that are the poles, all the zeros, m of z must contain all the zeros which lie on or outside the circle, and 1 minus m of z must contain all the poles which lie on or outside the circle of gp of z. Okay, so based on that my formula has become m of z is equal to 1 minus z inverse zi into bracket mk z raised to minus k plus mk plus 1 z raised to minus k minus 1 and so on, where k is always greater than or equal to n, where I have already defined n. 1 minus m of z is for 1 minus pj z inverse, 1 minus z inverse raised to p, 1 plus a1 z raised to minus 1 plus a2 z raised to minus 2 and so on. Here mk plus 1, a1, a2 are the variables, they are unknowns and we need to find those unknowns. Okay. Now the rules for solving this, we have two rules, basic rules and most important rules. First rule is that the order of m of z and 1 minus m of z should be equal or same. Okay, if the order of m of z is 3, 1 minus m of z should also have 3. Both of their orders should be same, and the total number of unknowns must be equal to the order of m of z. Okay, if the order is equal to the number of unknowns, then each and every value will have their own independent values, unique values. Okay, and we need to find the unique values. Okay, we don't want any linearly dependent values, we all want them to be linearly independent values. So for that, the order and the number of unknowns should be same. Okay, I have taken up a sum which will explain this formula in much simpler format. Okay, first you have GP of z given to you. Now as you know, your formula is in which form? Z inverse. Your formula is in the form of z inverse, so you need to convert your transfer function in the form of z inverse, which is this. My question was 0.01 into bracket z plus 0.2 into z plus 2.8 upon z into bracket z minus 1 into z minus 0.4 into z minus 0.8. I converted it into z inverse format. I got 0.01 z raised to minus 2 into 1 plus 0.2 z inverse into 1 plus 2.8 z inverse divided by 1 minus z inverse, 1 minus 0.4 z inverse, 1 minus 0.8 z inverse. As you can see, I have a 0, 2.8, that is minus 2.8, it lies outside the circle, and I have a pole which is at 1, which is lying on the circle. So GP of z has a 0 at minus 2.8 and a pole at 1, which 2.8 lies outside the circle and 1 lies on the circle. So m of z must contain the 0, that is 1 plus 2.8 z inverse, and 1 minus m of z should contain the pole, which is 1 minus z inverse. Okay, now what is this p? P is nothing but the order of your r of z or the order of z equals to 1 in the GP, whichever is greater. So I'll be using p as 1 over here, so I get 1 minus z inverse. Okay, because my order of the pole is 1 and also my input is also step input, so its order is also 1. So irrespective of whatever you consider, p is 1 over here. I won't be considering this because I am already considering this. This is considered when you have other poles other than 1. You have poles which are other than 1, that is outside the plane. This is only used for when it is outside the unit circle. This is used when the poles are on the unit circle. Okay, now none of my poles are lying outside the unit circle, so I won't be using this. These rules are used for truncating these equations. These rules are basically used for truncating these two equations. So based on this rule, I'm truncating this. I won't be using that, so I'll be only using ratio p is equal to 1. P is equal to 1, so I'll be using 1 minus z inverse raised to p, that is raised to 1. Okay, I've got this. Now I know what is m of z. M of z is nothing but 1 plus 2.8 z inverse. 1 minus m of z is 1 minus z inverse. Now what about these terms? How do I determine what I have to call over here? Okay, now that is determined by the order. Now what is the order of my poles over here, or the denominator? It is 3. Yeah, order of my denominator is 3. So I have to make sure that the order of m of z and 1 minus m of z is also 3. Okay, it should be 3. Now the next question that arises is, now I know that order of m of z and 1 minus m of z should be 3. Now I need to determine number of unknowns. I have said that total number of unknowns must be equal to the order. So I need only 3 unknowns. It shouldn't be greater than 3 or less than 3. The order is equal to the number of unknowns, and number of unknowns is equal to 3, and order is also equal to 3. So based on that, I need only 3 unknowns. Now how do I determine 3 unknowns? Number 1, order should be same. So I'll first determine 1 minus m of z or m of z. Now let us do one thing. I can put k greater than equal to n, where n is equal to 1. Okay, over here n is equal to 1 now. Because I have 1, 2, 3, 4 zeros, and 1 2 3, 3 poles. 4 minus 3 equals to 1. I have n is equal to 1. Number of poles minus number of zeros, so n is equal to 1. I know my n is equal to 1, so k can be anything greater than equal to 1. So I can take k is equal to 1. I can take k is equal to 1. So from that I can also write m1 z inverse plus m2 z raised to minus 2. This will also give me the same thing. Like, I'll write this properly. I can write m of z is equal to 1 plus 2.8 z inverse into m1 z raised to minus 1 plus m2 z raised to minus 2. This will also give me maximum order 3. This will give me maximum order 3. If I write 1 minus m is equal to 1 minus z inverse, this term I have already explained how to get. Now for this we also need order to be 3, so I'll only take till here. So I'll take 1 plus a1 z raised to minus 1 plus a2 z raised to minus 2. When you open up these brackets, you get maximum z raised to minus 3 in both the terms. So that will determine that my highest order is 3. But how many unknowns are there? 1, 2, 3, 4. I have 4 unknowns, but I have already said I need only 3 unknowns. Okay, that's the issue. So I need to determine. What I need to determine is that I need only 3 unknowns because my order is 3. So I cannot neglect this. I cannot omit anything from here because there is no condition over here which tells me that I can omit this, but there is a condition over here. I can write directly k equals to 2. I can say 2 is greater than 1, right? So I can take k equals to 2. So I can write m2 and z raised to minus 2. I can directly write that. Instead of starting from 1, I can start from 2 also. That is in my hand. Okay, so based on that, now I have 3 unknowns and order is also 3. So because of that, I have taken m2 and z raised to minus 2 instead of taking from k equals to 1, that is m1 z raised to minus 1 and m2 z raised to minus 2. I have taken directly m2 z raised to minus 2. The reason is simple and only thing is that I need to satisfy these 2 rules. Rule number 1, both of their orders should be same. M of z and 1 minus m of z, both of their orders should be same. Second, total number of unknowns and the order should be same. So I know that order is 3, so my total number of unknowns should also be 3. I know that in the 1 minus m of z, I get order 3. There is no way I can truncate this, but there is a way in which I can truncate m of z. So I have truncated in m of z and made sure that its order is also 3. From there I get 1 unknown. From the below equation I get 2 unknowns. So total 3 unknowns and order is 3. Okay. Now based on that, I am equating the 2 equations. I know what is m of z. I have opened up the brackets. I know what is 1 minus m of z. I have opened up the brackets. I have kept m of z on the one side, all the other terms on the other side. I have now found m of z for the second equation. I am equating this equation and this equation, both of them, and I am finding the values. So I have 0 z inverse plus m2 z raised to minus 2 plus 2.8 m2 z raised to minus 3 from my first equation. That is equal to z inverse into bracket 1 minus a1 plus z raised to minus 2 a1 minus a2 plus a2 z raised to minus 3 from my second equation. From this I can see that 1 minus a1 is equal to 0, a1 minus a2 is equal to m2 and a2 is equal to 2.8 m3. Using that equations I found out a1 is equal to 1, m2 is equal to a1 minus a2 and 2.8 m2 equals to a2. So I substitute the value of a2, that is equal to 2.8 m2 in this equation. Okay, I know a1 is equal to 1 from here. I know what is a2. I substitute those values and I found out the value of m2. I substitute the value of m2 in this equation and I found out the value of a2. So I found out a1, m2, a2. Found out those values. I substitute those values in this. I found out m of z, 1 minus m of z. So I got what is m of z. I got what is 1 minus m of z. Both of their values are known to me. I'll directly substitute them in dc of z, that is 1 upon gp of z into m of z upon 1 minus m of z. Simplify the equation, you will get dc of z, which is equal to 26z into bracket z minus 0.4 into z minus 0.8 divided by z plus 0.2 into z square plus z plus 0.73. This is my deadbeat controller. Okay, now remember one thing, again I'm telling you, the truncation is in your hand. The truncation of the formula is in your hand. You need to make sure that the order and your total number of unknowns should remain same. Based on that, you can truncate them. You can truncate this formula based on that. Okay. Now C of z is nothing but r of z into m of z. Just substitute the values of m of z. That is only this equation. We don't want 1 minus m of z. We only need m of z. We'll substitute the value of m of z in this and find out C of z. Okay, you'll notice that C of z only has those poles and zeros which lie on or outside the circle. Okay, those poles and zeros only. I have another sum which will explain this truncation even much better. Okay, the second sum is like I have GP of z which is equal to 0.0004 into z plus 0.2 into z plus 2.8 upon z minus 1 the whole square into z minus 2.8. I have converted this in the z inverse format, which gives me 0.0004 z inverse into 1 plus 2.2 z inverse into 1 plus 2.8 z inverse divided by 1 minus z inverse square into 1 minus 0.28 z inverse. Now I have 1 0 at 2.8 which lies outside the circle, and I have 2 poles which lie on the circle, that is at 1. Okay, 2 poles lie at 1 and 1 0 lies outside the circle. So m of z must contain 1 plus 2.8 z inverse, and 1 minus m of z should contain 1 minus z inverse the whole square. So over here I'll write p is equal to 2 because I have to write the highest order either of r of z or of z equals to minus 1. So z equals to minus 1, the order is 2. So that is the highest value. So I'll use 1 minus z inverse the whole square, and for m of z I'll write 1 plus 2.8 z inverse. Now again the denominator's order is 3, square and 1 order is 3. I have 3 poles and 1 2 3 3 zeros. Okay. So again I know my n will be equal to 1 over here. M of z will be equal to this. Now I need to define 3 unknowns. I know my order is 3. For m of z and 1 minus m of z the order will be equal to 3, and I need to determine how many which unknowns do I have to use. Now for 1 minus m of z I have 1 minus z inverse the whole square. So from here I get order 2. I need only 1 z inverse which will make it order 3. So I'll only use 1 plus a1 z raised to minus 1. That's it. I won't be using plus a2 z raised to minus 2 because that will make the order 4. I need to only make it order 3. So I'll only use till here. So from this I get that I have obtained one unknown from here. Okay. So based on this one unknown I'll make m of z which will have 2 unknowns. So in this case I will use k equals to 1, and from there I'll write z raised to minus 1 and z raised to minus 2, from which I'll get 2 unknowns. Okay. So it changes from question to question which variable, which m of z or 1 minus m of z will have the 2 variables or 1 variable or 3 variable. Okay. We have to make sure that first we satisfy the order, and once we satisfy the order, based on the order it will decide which variables are to be included and which to be excluded, how to truncate it. Okay. So from here I have determined from using 1 minus m of z, based on 1 minus m of z I have determined which m of z's which variables to be used in m of z. Whereas in the earlier question, based on m of z I had determined how many variables to include in 1 minus m of z. Okay, same thing again, we'll combine the two equations, find m1 a1 m1 and m2, which I get a1 is equal to 1.28, m1 equals to 0.72, m2 equals to minus 0.46. Based on that I find out my equation for m of z and 1 minus m of z. M of z comes about 1 plus 2.8 z inverse into 0.72 z inverse minus 0.46 z raised to minus 2, and 1 minus m of z comes to 1 minus z inverse the whole square into 1 plus 1.28 z inverse. Okay. The next method is the same. Find dc of z, that is 1 upon gp of z into m of z upon 1 minus m of z. Find dc of z, which comes about 1800 into z minus 0.368 into z minus 0.28 upon z plus 0.2 into z plus 1.8. C of z comes over, C of z is equal to r of z into m of z. You know what is m of z from here. You substitute this value of m of z into the equation and find out C of z. I have not done the Taylor's and Lawrence series in this expansion. as I find it too tedious. You can go ahead and do it, no problems with that. So that's all about Deadbeat. Please make sure that you do the truncation properly, because the main thing over here is the truncation. Once you do the truncation properly, then everything is the same as before. The only issue when your poles and zeros lie on the circle or outside the circle is the truncation part. Okay, if you have any issues or doubts, or something is not clear, please comment in the comment section below, and I'll get back to you as soon as possible. Thank you very much.